Hello, welcome to day 5 of units 1 and 2, the last day in the unit. Today we'll be talking about the chain rule, which I believe you've seen from pre-calculus honors, and also differentiation of trigonometric functions, including sine, cosine, cotangent, cosecant, tangent, and secant, and the such. But first we have a warm-up, so let's take a look. The warm-up is asking or telling us that we have a function f and that it is continuous, and it is continuous on a closed interval, -3 to 6. And then it tells me that if f of -3 is -1 and f of 6 is 3, then what is it that the IVT guarantees? That's the intermediate value theorem. I believe that was from day 2. So if you need to reference your notes from day 2, go ahead, but take a minute. All right, let's talk about this. So the IVT is that theorem that says if I have a continuous function on a closed interval, and I'm looking for an output value, okay, between the endpoints of my interval, it's guaranteed to exist, or it guarantees that there is an x value on the interval that will take me to what I'm looking for. Okay, so the IVT again guarantees the existence of an x value, an input, right? They call it C in the theorem. Guarantees that C, there is a C value such that f of C equals some number between the inputs of, between the endpoints of my range. Okay, so the first thing I'm going to go through here is find everything that is telling me between -1 and 3, because that's not what the IVT is talking about. The IVT again guarantees the existence of a input between -3 and 6, between the interval -3 and 6. So B can't be the answer, because it's saying that there's something between -1 and 3, which are the endpoints of my output. Okay. It does not guarantee that the particular C value, that it doesn't tell me what the C value is. So even though it might be true that there is a C such that f of x is, or f of C is equal to 0, we don't know that C is 0. So this isn't necessarily true. It could be the case, but it doesn't have to be true. The IVT does not guarantee that. Okay, IVT does not guarantee us anything about the slopes. Okay, and this is saying that that there is some constraint on my outputs that f of x has to be between -1 and 3, and that's not the case. F of x could be doing all sorts of crazy things in between -3 and 6 on its way from -1 to 3, but that doesn't mean that the value of the function is limited to those y values. Okay. So just by process of elimination, we see that yes, in fact, there's at least one C on the interval from -3 to 6, right? There's at least some input between the closed in the closed interval that will take me to a number, okay, an output between the endpoints of the output, and one is between -1 and 3. This number could have been anything between -1 and 3, and IVT guarantees that it exists. Okay. For instance, up here, like I was saying, we don't know what the C value is that gets me there. We could figure it out, but it doesn't guarantee that it is a unique or a specific value. Okay. All right, so first things first, we want to make sure that everybody is aware of the basic trigonometric functions and their derivatives. And that's why I said maybe. I'm pretty sure most of you had seen this in pre-calc honors through talking with Miss Reiser. What?
You didn't introduce and say, today we're doing lessons 2.
I did that when you were sleeping.
Oh, I'm sorry to interrupt you then. I just wanted to help.
I know.
I'm sorry.
It's okay. I appreciate it. Thanks. Hey, kitty. Meow.
Okay, focus.
Okay, so first things first today, we want to make sure that everybody is aware and familiar with basic trigonometric functions and their derivatives. That's why I said maybe review, because I'm pretty sure that through talking with Ms. Reiser, Ms. Giro, that everybody's been introduced to these if you take pre-calc honors. If you're coming from a different school or from out of state or maybe from not pre-calc honors, just regular pre-calc, maybe you hadn't seen this. But it's pretty straightforward. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of secant is secant tan. And the derivative of cotan is negative cosecant squared. And the derivative of cosecant is negative cosecant cotan. Now, I know that seems like a lot of information to just know and be able to recite, but these should be pretty easy, sine and cosine. And then I have a little trick for these two. So if you can just remember T, S, S, and then CT negative, CS, CS, okay? Make that T look more like a T. Then all you have to do is circle stuff to remind you. So the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is tangent secant or secant tan. And the derivative of cosecant is negative cosecant cotan or negative cotan cosecant. Right, because multiplication is commutative. Okay, so the chain rule. I've written it out sort of two different ways, and then there's the layman's term, derivative of the outside times the derivative of the inside, which makes things very simple, but sort of overlooks some of the subtleties of what's really going on with the chain rule. So here's a way that maybe you've seen it, right? The composition of f of g, the derivative of f of g is the derivative of the outside with g inside times the derivative of the inside, right? G was the inside. The Leibniz notation would look like this. We let some function y equal f of g of x, okay? And we'll let u equal g of x. So then y is equal to f of u. Then the derivative of y with respect to x, okay, is the derivative of y, or f, with respect to u, times the derivative of u with respect to x. And when we multiply these together, the du's cancel, and I'm left with dy dx. Okay? But again, you are maybe more familiar with it as the derivative of the inside, or excuse me, the derivative of the outside times the derivative of the inside, which is perfectly fine for computation purposes. All right, first up are a few examples involving just the trig aspect of today's lesson. So here we do have a product. So product rule is going to come into play. Okay, so P prime of x is equal to the first times the derivative of the second plus the second times the derivative of the first. Notice how I like to leave room at the beginning when I do that last part so I can squeeze in the single term. All right, over here, g of theta. Let's use a different color since we're sort of far over. Let's see, g prime of theta be the derivative of the first. Remember, the derivative of cotan is negative cosecant squared plus the derivative, plus a product. So product rule is going to come into play, which is first times the derivative of the second plus the second times the derivative of the first. Alright, let's clean things up a bit just so that we can see what our final answer is. That e to the theta can come out. And I'm left with secant squared plus tangent minus cosecant squared. Okay. So example number 2 is our first example involving the chain rule. Okay? For this first example, first part of example 2, I'm going to actually write out what my functions are and where they are, right? So this is going to be my inside function. That's my g of x. Or, for those Leibniz people, u. Okay? And then the stuff to the fourth power is my f of x. And let's just, for the purposes of this example, call that y equals x to the fourth. Okay? So big G of x is equal to f of u, which is u to the fourth, and the derivative of big G of x is let's see, dy du. Okay. So the derivative of this with respect to u, which is just 4 u to the third, okay, times the derivative of u with respect to x. This was u. And the derivative of that will be 3x squared minus 2. Now there's one thing we have to take care of. We don't want u's in my final answer. So there would be my final answer. And if you go back up here and look and just sort of use that derivative of the outside times the derivative of the inside, you can see that all I've done is drop the 4 down and decrease the power by 1, leaving the inside the same. And then I multiplied by the derivative of that inside. Okay. In the next part, I'm not going to write all this out, and I'm just going to do, like I said, derivative of the outside times the derivative of the inside. All right. So the derivative of my outside will be 1/5 okay. 1/5 decreased by 1 would be -4/5. Okay. Then multiply by the derivative of the inside, which is 0 plus cosine t. And we're done. There's nothing that I see worth trying to simplify. Alright, so in this example, we're asked to write the equation of a line tangent to the curve at a given point. So we did this last class, or we did this in the last video, but this time we're just introducing some ideas of trig and some chain rule. So the first thing I need is the derivative, which in this case is 1 plus negative sine x. So we'll make that a minus sine x. Okay. And then I want to know what the slope is at 0, 1. So when x is equal to 0, sine of 0 is 0. Okay. So my slope is 1. So the equation of the line, 1 minus 1, equals x. Okay. Part B, y prime is equal to cosine x. Cosine of 2x actually has a chain rule involved because the 2x inside is not just x. You could think of everything as having chain rule involved. This would be the derivative of the outside is cosine x and the derivative of the inside is just 1. But in this case, the derivative of the inside is more than just 1, it's 2. So I do have to use chain rule here. So the derivative of the outside gives me a negative sine 2x. Okay. And then I'm multiplying that by the derivative of the inside, which is 2. Okay. Now we want to know what's the slope at this point, so I'm using that x value of pi over 6. Okay, let's see. Pi over 6 is what, 30 degrees? So the cosine would be rad 3 over 2. Minus 2 times the sine of 2 pi over 6, which is pi over 3. So sine of 60 degrees is same thing, rad 3 over 2. Okay. And the reason I plugged in 2 pi over 6 here was because it was sine of 2x. Right. Okay, well, the 2's cancel there. And, actually it's much easier to just do this. I have 2 rad 3's over 2, and I'm taking them away from 1 rad 3 over 2, so I should just end up with 1 negative rad 3 over 2. Righto? Alright, and so my equation is going to look like y minus 1 equals negative rad 3 over 2 times x minus pi over 6. I think that radical sign looked more like a radical sign. Alright. So, just to reiterate, there was a chain rule here because what was inside the function cosine was more than just x. It was 2x. That's where the extra 2 came from. And when I plugged in pi over 6 into sine, instead of getting a sine of 30 degrees, which is 1/2, is actually sine of 2x. So it ended up being the sine of 60 degrees, which is rad 3 over 2. So for the last example, a little bit of a conceptual question. What are the values of x, or what values of x does the graph of y, being the function g of x, is x plus 3 cosine x, when does that have a horizontal tangent? So the first question that we have to ask is, what does it mean to have a horizontal tangent, right? That's something that we haven't really talked about. We should know that horizontal lines have slopes of 0. So I'm really asking the question, when is g prime of x equal to 0? Right? So g prime is 1 minus 3 sine of x. Okay? And then letting g prime of x equal 0, we can solve to get that sine of x is equal to 1/3. Okay, so for what values of x does the graph have a horizontal tangent? Values of x that are equal to the arc sine of 1/3. Right? Now, that's going to give you 1 or 2 values, but there are an infinite number of places where this occurs, so we would have to multiply by the period, 2 pi? Nope. Let's see. Sine is going to be the same every pi. Plus pi k. Right? Alright, so that's it for today. That's actually it for the unit. When you come in next class, we'll have a short activity and we will review for the test. And then the class after, we'll have a test. Yeah, so thanks for watching.